All right, so let's start by reviewing what we've learned last week. Okay. So we've introduced a few important definitions, starting with the one with the graph. Okay. So recall that a graph consists of two sets. First, you have to have the vertex set. All right. So depending on the context or the application you're considering, vertices can be like social networks. For social networks, it can be like user accounts, okay? But for computer networks, it can be any devices that are able to communicate with other devices, okay? And then you have edges. So edges describe like a binary relationship between different vertices, okay? So by binary, I mean for any two vertices, either there's an edge or there's no edge, okay? And of course, we've considered the case where edges have weights. So in that case, it's not just a binary relationship, okay? So because now you can assign numbers. Right? But for most part of this course, edges don't have weights, okay? And a few important terminologies, so like endpoints. So given an edge, the two vertices here, they're called endpoints, right? So we also discussed like neighbors. So if A is B's neighbor, then this means there's an edge between them. And in this case, we can also say that A is adjacent to B or B is adjacent to A, okay? And to describe the relationship between an edge and a vertex when they are like connected to each other, we use the word instant. All right. So an edge is instant to a vertex, like an edge E is instant to A. Okay. Okay. So I think probably the most important definition we've discussed last week is about connected graph, where we actually discussed two different yet equivalent definitions. So the first one is that, if I recall correctly, it's by Melvin. Okay, so Melvin suggests that if you can find a spatial vertex which acts like a hub, where you can, starting from the spatial vertex, you can go to or reach any vertex in the graph. Okay, so this guy, this vertex V, is the spatial guy. Okay, so this is like the first definition, and then we've come up with the standard definition for connected graph. So in this definition, you have two vertices. So actually, you have to consider any two vertices in a graph. And you have to show that there's always a path, no matter which vertices you choose. Okay? So this is connected graph. Okay? So we spent some time discussing why these two definitions are equivalent. Okay? And also a component, all right? So a component is a maximal connected subgraph, okay? So in this graph, we have three components, okay? And degrees are just the number of vertices, the number of neighbors of a vertex, okay? So in this case, the degree of U, since U is adjacent to 1, 2, 3, 3 vertices, so U has a degree of 3, all right? All right, so I think this part, we consider the relationship between minimum degree and whether we can ensure that the graph is connected based on the minimum degree, okay? So recall the minimum degree is just like the smallest degree among all the vertices in the graph. So in this graph, the smallest degree will be the degree of this vertex, all right? So this one has a degree of 2, meaning the graph has a minimum degree of 2. Okay. So I think the first trivial property we've discussed is that if the minimum degree is n minus 1, recall that n is just the number of vertices in the whole graph. So if the minimum degree is n minus 1, this is like the highest possible degree you can get in any graph given n vertices. So this is actually a complete graph. So apparently this is a connected graph, okay? Because recall that for a graph to be connected, you have to show that for any 2 vertices in a graph, there's a path, okay? So this is not just a path, okay? This is actually an edge for any 2 vertices in a graph. So obviously, this is a connected graph. All right. And then we discuss, we decrease this minimum degree, okay? Now we know that n minus 1 is like super high, meaning that there are lots of edges in the graph. So naturally, the graph will be connected, given that this degree is like super high. So we want to lower this degree to see like what is like the smallest possible value here. But still, we can guarantee to have a connected graph, right? How about n minus 2 or n minus 3, okay? So we just cut the n minus 1 into half, okay? So we consider n over 2. So it turns out that even if the minimum degree is just n over 2, it's still connected, okay? And we've given a proof based on contradiction, okay? But as I mentioned last time, this proof cannot reveal too much structural information about the graph. So today we're going to consider a different approach to prove the same argument, okay? Okay. So this is the original argument or the original statement, okay? But today now we're going to prove a stronger version, okay? So we're going to show that if the minimum degree is n over 2, then for any 2 non-adjacent vertices. Non-adjacent vertices means that these 2 edges, they are not neighbors, okay? There's no edge between them. So like these 2 guys, U and V, okay? There's no edge between U and V, right? So they are not neighbors. But they do have common neighbors, like this W. So W is a neighbor of U. Also, W is a neighbor of V. So W is like a common neighbor for U and V, okay? And if U and V have a common neighbor, obviously U and V have a path, okay? They can use W to reach the other endpoint or the other vertex, okay? Okay, so I think this is what we're going to do first today. We're going to show that under this condition, where the minimum degree is like still very high, okay, n over 2, it's still a very large number. But anyway, we're going to show that under this condition, for any 2 vertices, another way to put this is that for any two vertices, either they are adjacent or they have a common neighbor. Okay, that's a different way to describe the same thing. Okay, so I can change this to this. Okay. So it's like for U and V, there are two possible outcomes. Either they are neighbors or there's a common neighbor. Okay. These two outcomes can happen at the same time. Okay. So this means it's possible that U and V, they have an edge, and also they have a common neighbor. That's possible. Okay. So that's why I did not write like either or. So it's just or. So both can happen. Okay. Okay, so this statement, I think, reveals more structural information compared to this one. Okay, because this one just tells you that this is a kinetic graph. Okay, nothing more. But this statement shows that actually for any two vertices, the distance between them is at most 2. Like the shortest distance between them is at most 2. Okay. Okay, so now we're going to show this. Okay. Any idea to show this? 大家想到要怎么说明这件事吗？所以我们已知的条件就是最小的 degree 是n除以2 ，OK， 那要完全根据这个条件，只根据这个条件，就可以看得出来说，对于任两点，他们要么就是直接有一个 H 连起来，啊，要么他们有一个共同的邻居。所以有没有人想到这要怎么证？有什么方法？大方向。Okay, so for this course, there are like two, yeah, I would say just two proofs techniques that we're going to use a lot. Okay, first one, proof by contradiction. Okay, and second, proof by induction, 数学归纳法. Okay. So last week we've used proof by contradiction. Today we're going to still use proof by contradiction. Okay. Okay. So whenever you want to prove some statement using using contradiction, first you have to assume the statement that you try to prove is wrong. And then try to find some contradiction. So what happens if this statement is wrong? 如果我们要说的这句话是错的，那代表什么事？You can consider this one or this one. They are the same. Okay. So the overall structure is like if P, then Q. Right? So we have this if something is true, then something will happen. Okay? So what's the negation? Negation is like the statement, but it's wrong. Okay? Okay, negation. So what's the negation of this statement? So if P, then Q. 若 P 则 Q， 若 P 则 Q， 如果是错的，那代表什么事？Okay, let me give you a few choices. Okay. So now we're considering the negation. Okay. Okay. So the first choice, if P, then not Q. Okay. Okay. So which one is correct? 所以若 P 则 Q， 然后如果这是错的，我要找到这 negation。OK。所以这句话跟下面这4个哪一个是一样的？都是代表若 P 则 Q 是错的。3. Okay. Right. So 3 is the correct answer. But why? 所以答案是3。那有人可以知道为什么吗？So if this statement is wrong, if P then Q, if this one is wrong, this means even if P happens, Q does not happen. If P 发生了，但是 Q 没有发生。P 成立，但是 Q 没有成立。OK， 所以就这个，就 P 成立了，但是 Q 没有成立。OK， 所以这就矛盾。OK。所以你可以把它想成，比如说，如果考试考100分，就出去玩啊。考试考100分出去玩，那如果这句话是错的，代表什么？你考100分，但是你没有出去玩，这是唯一矛盾的。你如果考100分，你如果没有考100分，能不能出去玩？还是可以。OK， 你如果没有考100分，你也可以不出去玩，你也可以出去玩，都可以。所以关键会让这个错就只有一个 case。就是你有考100分，但是你没有出去玩 ，OK， 就是这个 ，OK， so for this statement, what is P? Okay, so this is P. And this is Q. Okay. So now, according to our strategy, we're going to show this, prove this by contradiction. So we're going to assume P is still true. Okay, the minimum degree is still n/2, but now Q is wrong. Okay, so now we have to find the negation of Q. So what's the negation of Q? 所以如果 Q 是错的，那代表什么意思？ Right, so if you consider, yeah, or if you want to stick with this, the statement here, you can say that there are two verses U and V, okay? So this is the first difference. So in this statement, we say for any, okay? Like, or for all. But if you want to show that this is true, or this is wrong, all you have to do is to find one instance. In this particular example, this means we have to find two vertices that violates this constraint, okay? So that's why Melvin said that there exist two vertices U and V such that U and V are not adjacent and U and V do not have a common neighbor. Okay? Okay.所以刚刚的关键是本来的这个Q， 我们要找到它的，他是说它是错，就是找到它的 negation。所以这边本来是要说，哎，对于任两个点，它都会满足下面这个性质。OK， 那如果我们今天要说这个是错的 ，OK， 你本来是说全班每一个人都考100分，你如果要说明说这句话是错的，你只需要找到一个人他没有考100分。OK， 或者说对全班任两个人，他们的分数加起来都会超过180。如果你要说这句话是错的，你只需要找到2个人，他们的分数加起来没有超过180。OK。Okay, so this is the first difference. And the second difference is that you see that there's an OR here. So we use OR to combine two conditions or combine two constraints. So whenever you want to find the negation of OR, A or B, okay, you have to take AND. Okay? OK， 所以举例来讲，比如如果说 某一个同学他是，应该说班上同学要么都是从高雄来的，或者都是从台北来的。如果这句话是错的，那就代表说班上同学我们不要讲很多人，就讲一个人好了，就假设叫我好了 ，OK， 我是从高雄来，或者是从台北来的。如果这句话是错的，那就代表我既不是从台北来的，也不是从高雄来的，所以这边会变成这比较像是也的意思 ，OK。但 anyway 就是你要把 or 变成 and，OK。所以以这个例子来讲的话 ，UV 它就变成是。Okay. So we use these two nots to take the negation of these two conditions. Okay, now we can put this all together to find the negation of this statement, okay? So we will assume the negation holds, which means we assume the minimum degree is, I think I'll change this equal to at least, okay? Assume the minimum degree is at least n over 2, and we can find two spatial vertices. Such that they are not adjacent, and they do not have a common neighbor. All right, okay. So this is our assumption, okay? And now we want to find some contradiction, okay? So let me first draw the whole picture, okay? First, I'm going to draw the set of U's neighbors. I'll call this capital N of U, or just NU. So this is the set of neighbors of U, or set of U's neighbors. Okay? So now Okay, we have some verses here. Those are use neighbors. Okay. Next, I'm going to draw the set of neighbors of V. Okay. So now I have a question for you. So suppose I want to draw the set of V's neighbors. Can I draw it like this? So why not? Exactly. So because we know that U and V, they do not have a common neighbor, so there's no intersection or common elements between these two sets. Okay, so these two sets are disjoint. Okay. Now, I have to draw U. Okay. So is it possible that U is also in this set? Can I put U in this set? 我可以把 U 画在这个 N of U 里面。So why not? So U is not adjacent to itself. Okay, so because this set is U's neighbors, okay, but U itself cannot be its neighbor, okay? So there's no self-loop. A self-loop is like this. So this is a vertex U, and there's an edge like this, okay, with both endpoints being U. So this is not allowed for this discussion. So U cannot be in this set, okay? So how about this set? Can I put U in this set? 可不可以把 U 放在 N of V 里面？我们先确认 U 不能放在这里面，那 U 能不能放在这里 ？OK， 为什么不行？ Exactly. So if U is in this set N of V, this means U is a neighbor of V if U is inside this set. Okay, because every vertex in this set is a neighbor of V. Okay, so if U is in this set, then U is adjacent to V, which is impossible according to this assumption. Okay, so U cannot be in this set, which means U cannot be in any of these sets. So we can put U here, okay? And now we know that U is adjacent to this set, okay? So similarly for V, we know that V cannot be in this set because we do not allow self-loops. And also V cannot be in this set because otherwise U and V will be adjacent, which contradicts to this assumption. So we have V here. All right? Now this is just part of the graphs, okay? Because there can be other vertices that are not adjacent to U or V. So I didn't draw the whole graph, okay? But still, looking at this picture, there's a contradiction. 对，大家可以看出矛盾在哪里吗 ？OK， 所以矛盾在哪里？ Yeah, but as I just mentioned, I didn't draw the whole graph. So maybe there are some vertices here, and these vertices are adjacent to this set and also this set. Then this graph will be connected. Yeah, So this is not a whole graph. Yeah. So why? So exactly. So you're going to see that the number of vertices for the graph, even it's just some part of the graph, still the number of vertices is greater than n. And recall that n is the number of vertices for the whole graph. Okay? So that's impossible. But why?
Because the minimum degree is more than n/2, so nu plus n
Is already n
and
plus UMV. Exactly. So far, to construct this graph, okay, which is part of our proof, we've used these two assumptions. Okay? So recall that for any proof, you have to ask yourself, have we used all the assumptions? Okay? So at this moment, we haven't used this. Okay? We didn't use the assumption that the minimum degree is at least n/2. So if the minimum degree is at least n/2, this implies that this set, the set of these neighbors, this set cannot be too small. Okay? It's actually quite large. The size is at least n/2. Okay? Now, we have n/2 here, n/2 here, and we know for sure that these two sets, they do not have intersection. So to compute or to count the number of vertices for these two sets, we can safely just add them up. There's no overlapping. Okay? So n/2 plus n/2 plus 2. Which 2? U and V. So similarly, because we know that U is not part of these two sets, similarly V is not part of these two sets. So again, there's no double counting. We can just safely add all these four numbers, okay, to get the number of vertices. So the number of vertices okay. So this is impossible because according to our definition, n is the number of vertices. Now you have more than n vertices, okay? So this is wrong, okay? So which means this is, this means that we've done because we proved by contradiction, okay? Okay. All right, so, but if you think about this for a moment, then you'll see that in order to get a contradiction, all you have to do is to get n plus 1, okay? As long as you have one vertex, one more vertex than n, then you get a contradiction. So, but now we have n plus 2. Okay, so this means that there's still some room for improvement, okay, to improve our statement. Recall that last week we discussed when the minimum degree is n minus 1, now we lower it to n/2. So it turns out that at least according to this proof, we can still lower this value. So can you see how? to get the exact or correct number. 所以我们这边算出来的得到的是最后会有 n 再加上2个 vertex， 但是你如果要矛盾，你事实上只需要 n 加1就可以了 ，OK？ 所以你不需要到 n 加1，你只要 n 加1就可以了。那我们要把我们本来的 statement 要做什么样的修改，可以让它变得更好，可以让它捕捉到更多的 graph， 让它的 statement 可以 apply 到更多的 graph，OK？ 然后这整个 proof 一样会 work。所以我们可以去怎么样修改这个 statement。Or let me think this way, okay? So how to make this number m plus 1? You cannot change this 1 here because this is for u. And you can also not change this 1 here because this is for v. But you can change these two numbers. Okay? These are the minimum degree. Okay? So there's still space for lowering this minimum degree. So, but still these two numbers, they have to be the same. So how to change this? So you can change it to m minus 1 over 2. Then you'll get m plus 1. Still a contradiction, okay? But now, you know that this will become m minus 1 over 2. And now we get, I would say, better statement because the minimum degree is lower. And once again, I should change this to at least, okay? So now this statement can capture more graphs because now the threshold for the minimum degree is lower, okay? So for example, if you can put, let's say n is 5, okay? So n is 5, n over 2 is 2.5. But if, because now we're considering degree, okay? Degrees must be whole integers. So greater than or equal to 2.5 means the minimum degree is at least 3, okay? But now if you change it to m minus 1 over 2, now suddenly you can consider graphs with minimum degree just greater than or equal to 2, or greater than or equal to 2, okay? 所以本来你的 statement 只能用在那些 degree 要有点大，就是比如说5个点的情况下，就是它真的派到这个 degree 是3的 ，OK？ 那现在就可以 apply 到 degree 是2。所以我们最后的 so our final result will be m minus 1 over 2. Okay. And the reason we can get this result is because first we have the proof. And then we look at the proof and see whether there's a space for improvement. And it turns out that there is indeed a space where we can lower this minimum degree. So it turns out that we get a better result. Okay? 所以我觉得刚刚那个过程，当然某种程度是我有点人为的去 营造刚刚这个过程。但是我要说的是，很多时候你一开始想要证的，其实不是最好的结果。OK， 你有机会，你把你本来的东西证出来之后，再去检查你的 proof， 然后你会发现，其实你一开始要说的那个你想要证的东西可以变得更好，用同样的 proof 的方法。OK。所以，因为至少对我来讲，我会觉得 n 减1除以2没那么直觉，因为这个减1有点怪怪。OK， 对我来讲 n 除以2是比较直觉的。OK， 那你会发现在刚刚的那个证明里面，如果是 n 除以2的话，就这里还是会让你有点空间可以做改善。OK。OK， 所以有问题吗？所以刚刚的 proof 就讲到这边。所以我刚刚就是想要传递两个资讯，第一个资讯就是在算 negation 的时候，就应该说在用 proof by contradiction 的时候，如果你的 statement 是比较复杂一点 ，OK， 那你就记得再去看，当我们用反证法的时候，就要比较小心一点，去看一下当它是错的，是代表什么意思 ，OK。然后第二个就是每一次比如说你在写论文的时候，你需要去证明一些东西，那你证明出来不一定是结束 ，OK。你证明出来，你可以再去回头看一下你的 proof， 看一下，是不是同样的方法可以有得到一开始更好的结果，这样子 ，OK。所以证明结束不是整件事情的结束。OK， but can we get an even better result? Can we still keep reducing this value here? Now it's m minus 1 over 2. Can we change this to n minus 2 over 2? So why not? So you should definitely ask yourself this question. So now you get a result. Can I get a better result? Okay. So if you cannot, then this means now it's safe to stop here, okay? Because there's no way pursuing a better result. So actually this is just this, okay? N over 2 minus 1. Okay. So is this true? To show that some statement is wrong, you don't need to write a proof. All you have to do is to find a counter example. 要找到反例。你要说一个 statement 是错的，很简单，你只要找到一个反例就可以。So, what's a counter example for this statement? So this is not difficult, okay? So you should try yourself. Say n is 6. So n is 6, then n over 2 minus 1 is 2. So the minimum degree is 2. And the minimum, and there are 6 vertices with minimum degree 2. Is this always true? Or even simpler, can you find a disconnected graph? If you have a disconnected graph, then this will be a correct example. So find a disconnected graph. So this is the minimum degree. And find a disconnected graph. 6个点，每个点的 degree 至少是2，能不能画出一个不是连起来的图？来给大家稍微下课的时候想一下 ，OK， 没有很困难。All right, if you want some papers, you can get it here.
昨天要我找那个，我是有查到，就是现在有人就是用币的。它的可行性大概在80%。
闭源的模型是什么？
就是像 GPT 的。
它跟我昨天说的有什么？
就是要我查性能。
性能？
现在我有 N 加 MCP。
对，就但他们有 MCP。
有。
他们的 MCP 是可以做什么事？
它有。
对，他做什么事？他的 MCP 可以提供什么？
他做的就是会先让人将题目就转换成数学模型，然后这些数学模型就丢给 MCP 去。
可是它转成数学模型就没话说了，它就是再用一些烧逻辑就可以了，对吧？所以可是这个就可能要很花时间。
对。
对吧？
它这个就是这个步骤花头。
可是它的数学模型是转成像是线性规划那种linear program、mixed integer linear program 那种，是吧？对吧？可是这个就不是整个目标，因为这个就直接转就可以了。这个不是我想要做，我想要做 JSON。格式的转换我觉得不是很重要，对我来讲，我想要说的是，就是如果可以把它转成比较小的问题，然后我们的 MCP 是提供它解决这些小问题的方法。但至于它怎么把本来的问题拆成小的问题，那就是 LLM， 而不是直接整个问题丢进去丢给 MCP 上。他现在做的事情是比较是直接把整个 MCP 把这些整个问题丢给 MCP 就算了，他这么说不要。这个当然可以了，但我觉得就没有用到 LLM 它的推理的能力。但因为他就直接原封不动丢给别人算，丢给别人算。
这个转换的过程。
这个转算很简单。
可是会失败的过程。
那个不是我 care 的，对，因为如果某种程度你都可以把 prompt 格式化的写出来，要做这个转换，我觉得是很制式、很 routine 的东西，就对吧？甚至可以直接写一个程式就可以做到这件事情。如果你都有角色的格式去描述本来的input的话，所以我想要的不是这个，我想要的是 LM 真的有参加去解的这个过程，只是它会需要一些上 routine 去帮助它。对，那这些比较小的 routine 就是 MCP 提供的，它可以是任何一个，比如说最简单就是，比如说只要是这个 input size 小于10，这句话如果是 JavaScript 就是比如说小于10个 Java，如果是 Graph 的话就是小于10，那它就可以 call MCP server去解这个 但至于要怎么把本来上千上万个点转成或拆成很多个这种小城市，那个这个就是 LLM 需要去思考。我的想法是这样，而不是直接丢，因为直接就丢好像没什么好做。对啊，对，这样差不多。对，所以对这个方向大方向是对的，但是它的具体的处理不是我想要的。
我还没有想到就是这样做。
OK，所以我觉得关键字是 divide conquer， 就是 divide 是 LLM 做，但是 conquer 是 MC。等下中午有时间吃饭吗？问一下，我去哪睡觉？
我是哦，像很多老师有说他们来吗？
我不用，我不用，不用。那这样不然什么吃饭？还是不会讨论很久？
我觉得，因为我目前是大概上次讨论到，是我目前可以跟你讲我的方向，然后以及我有点好奇我这边要我的多久。
对啊，
我觉得应该不会太久，
不会太久。
我是希望大概20分钟内。
好，我是不知道，因为如果1点要当助教，我帮。
我应该去很快吧，就是那上面有些班
All right, so let's continue. Okay, so this is wrong, and we will find a counter example. Okay. Now to find a counter example, we need to create a disconnected graph, meaning we have to find a graph that have multiple components. Okay. And here we specifically want a graph that has 6 vertices. Now, if you have 6 vertices and you want to create a disconnected graph, which means you have to create 2 components. So I think naturally you want to have like a balanced components. So naturally I will do this. Okay. So one component has 3 vertices, and the other component also has 3 vertices. Okay. And the minimum degree is 2. Okay. So to create such a graph with minimum degree 2, you can do this. Okay. So every vertex here has a degree of 2. And we have 6 vertices, 2 components. Okay? So this is disconnected. Okay? So therefore, this is a counterexample. Okay? So you can also test this statement. So we can consider any 2 vertices that are not adjacent, like these 2 on the top. So clearly, so this is U, and this is V. So clearly, U and V, they do not have common neighbor. So this is a counter example. Okay. So this is wrong, which means the statement here, in some sense, is the best you can get in this form. Okay? You cannot lower this value anymore. Okay. Okay, so this concludes the discussion about minimum degree and kinetic graph. Before I start the next topic, I want to give you like a small warm-up. Now this is related to total degree. There's a simple property about total degree of a graph. Okay. So what's the total degree of a graph? You just sum up all the degrees, and that's it. Okay. So for this guy, the degree is 3, 3, 2, 4, 3, 3. Okay. So what's the total degree? I count 18. Am I right? Yeah, okay. So 18 is the total degree. Okay. And what's the number of edges in the graph? And recall that we use m, lowercase m, to denote the number of edges in the graph. So you can count, okay? So I count 9. So can you guess what is the relationship between these 2 numbers, the total degree and the number of edges? So 大家可以猜到 一个图所有的 degree 的总和，跟一个图的 edge 数有什么样的关系吗？至少从这个 example 看起来是2倍 ，OK？ 那为什么？为什么刚好是2倍？Yeah, so it's like there are 2 ways of counting the total degree. First, you can consider every vertex, compute their degrees, and compute the sum. That's one way. Another way is not to consider every vertex one by one. Instead, you consider every edge. Okay? So for example, when you consider this edge, you know that this edge, it contributes 2 degrees. 1 degree here and 1 degree here. Similarly, for this edge, it contributes 2 degrees in the total degree. So 1 degree here and 1 degree here. So every edge contributes 2 degrees. So the total degree is just twice the number of edges. Okay? Okay, so now we know that total degree is twice the number of edges. And we also know that the number of edges, it must be an integer, okay? So it cannot be like we have 3.5 edges. No, it's impossible. So whenever you have an integer multiplied by another by 2, this means the product must be an even number. So the total degree must be even. OK， 所以这边只是一些关于 degree 一些简单的性质，等一下我们会用到 ，OK。所以这边第一个性质是 total degree， 就是 edge 数乘以上2 ，OK。但也因为是 edge 数乘上2，然后 edge 数又是整数，所以我们就会知道 total degree 它一定是偶数 ，OK。到这有问题吗 ？OK， 应该蛮无聊的 ，OK。好，所以 the actual topic that we're going to consider today is called graphical degree sequence. Okay. So first of all, what's a degree sequence? A degree sequence is just a sequence of numbers. But now their physical meaning is that every number represents the degree of some vertex. Okay. So for example, for this graph, the degree sequence it can be 3, 3, 3, 3, 2, 4. Okay. Okay. So the order is not important. All we have to do is to just list all the degrees. Okay. That's all. Okay. Okay, but for this graph, we first have the graph, and then we get the degree sequence. What we're going to do next is like reverse it. Okay, so first we're going to have the degree sequence, and then we'll construct the graph. okay? Okay, so this problem is called graph realization problem. Okay. By search files, I mean okay. So by search files, I mean so given the degree sequence, now we know that it has n degrees, which means the graph has n vertices. So we have v1, v2, up to vn. Those are your vertices in a graph. And you have to create a graph in such a way that the degree of vi equals di. Okay? So that's what I mean by search files. Okay? So for example, if the input is 3, 3, 3, 3, 2, 4, then you can just output this graph. This will be a graph that satisfies the degree sequence. Okay. 所以我们要做的事情就是我会给你一些数字，这些数字是 degrees 当然就会看我给你几个数字就代表有几个 degrees， 那也就代表说我有多少个 vertex 你需要产生 ，OK？ 然后你需要确保说你产生出来的 vertex 还有加上去的 edge， 它们的 degree 刚好会跟你的 input 是一样的。OK， 大家对这个问题有不清楚的地方吗？ So one of the motivations to study this problem is that if you are doing research in network area like computer networks or social networks, usually you have to create some network topologies so that you can test some properties or you can test your algorithms. But one way to get these network topologies is like to find whether there are some real traces or real topologies on the internet. But still, sometimes you want to create more topologies so that you can test, okay? And perhaps you want to test or control some parameters for the graphs, like the number of vertices or the number of edges or like the diameter or the radius, anyway. So somehow you want to control the network topology so that you can control your experiment. So to do this, a method is that you first sample degrees from some degree distributions. So the exact degree distribution that you're going to use depends on your context or your application, okay? So perhaps you're studying social networks, then perhaps you want to use some heavy tail distribution, okay? So anyway, it depends on your context. But anyway, what you're going to do with the distribution is that you're going to sample some degrees from it. So if you want to have a graph that has say 1,000 vertices, all you have to do is to sample 1,000 degrees from the degrees distribution. Okay, that's step one. And step two, you create a graph. That satisfies the degree sequence. Okay. And then you have a network topology. Okay. Okay, but anyway, the point here is that how to solve this problem, okay? So first, perhaps we should first ask, is it always possible to create such a graph, no matter what the degree sequence is? 有没有可能，就因为这个问题是说，给你一个 input，就是很多 degree， 然后你要去建一个 graph。那我们可能要先想的是，不是要去想那演算法，是要想这件事情是永远都可以做得到，是不是给你任何的 degree sequence， 你都一定可以建得出那个 graph？ 所以大家觉得有没有保证，不管我的 degree sequence 长怎么样，都一定可以画出那个 graph？ 所以问一下这边的，所以这同学觉得有没有可能？知道这个问题吗？那觉得有可能吗？所以我这边谈的是任何的 degree sequence， 我都可以画出一个对应的 graph。你觉得有可能 ？OK， 那为什么？马上你可以再想一下，所以觉得有可能吗？任何的 degree sequence。我到目前为止完全没有任何限制。对，你说超过节点数量，你这边的超过是谁超过节点数量？对。Yeah. So, right. So, if any degree here is greater than n minus 1, then you know that this is impossible because given an n vertex graph, we know the maximum degree is n minus 1. So the maximum degree you can have is n minus 1. Anything higher than that is impossible. Okay? So that's one constraint. Okay? But now, suppose I tell you that the maximum degree is lower or is at most n minus 1. Is it always possible to find a corresponding graph? 我现在确保说每个 degree 都不会太大，都最多就是到 n 减1。So why?
Let's say there's a degree, there's a sequence is 3000.
3000, okay?
So because the first number is 3, so there must be and there's only 4 vertices, so there must be a vertex that's connect to every other vertex. So which means that every other vertex has at least 1 degree. Yeah, but the sequence is 000.
Right, right. So now we know that the maximum degree is at most n minus 1. And for this particular example, 3 followed by 3 zeros, we know that this is impossible because if you want to create a graph that, we're going to say that a graph that realizes, okay? A graph that realizes this degree sequence would look like this, okay? So you have 4 vertices because the degree sequence has 4 numbers. Now one of them has degree 3, which means we have to create 3 neighbors for this guy, which also implies that 3 other vertices must have a degree of at least 1, okay? So you cannot have 3 zeros here, okay? So this is impossible, okay? Yeah, so this tells you that even if the maximum degree is at most n minus 1, still, it's not a guarantee, okay? It's still possible that you cannot find a graph that realizes the degree sequence, okay? But how should I put this into like a general rule? So now the question is this, okay? So I want to solve this graph realization problem. But before that, I want to first test whether this is possible or not, okay? Okay, so a graphical degree sequence is a degree sequence such that you can find a graph that realizes it, okay? So for example, this 3, 3, 3, 4, 2 is graphical. However, 3, 0, 0, 0 is not graphical. Okay? And based on our previous discussion, we also know that if a degree sequence has a maximum degree that is greater than n minus 1, we know that this cannot be graphical, okay? Or this degree sequence is not graphical, okay? So before we can solve this question, okay, we want to first consider like a somewhat simpler question. So given a degree sequence, we want to determine whether it is graphical or not, okay? So we want to develop some kind of algorithm, okay? Because there's no simple rules that can be used to test whether a degree sequence is graphical or not, okay? But there are still some, I'll say, simple checks that you can do, okay? So we know that the total degree must be an even number. Therefore, if the degree sequence is like 3, 3, 3, 3, 3. So this is not graphical. Okay? Because we know the total degree must be an even number. Okay? So these are just some simple tests, but it is not a guarantee. So you cannot just use this check to answer the previous question. Okay, so this is very important. So 这边的讨论只是给大家一些练习，去感受一下这个问题在问什么 ，OK？ 然后我想大家在想这个问题的时候，可能都会想到一些简单的规则去判断说一个 degree sequence 是不是 graphical。比如说刚刚奕修有提到 maximum degree 是不是最多是 n 减1，然后total degree 是不是 even， 就这些都是一些很简单的 check。但是就算是满足这些 check， 也不一定就代表它就是 graphical，OK？ So I think you can also use this rule to rule out this example 3, 0, 0, 0 because the total degree is odd. Okay, but you can also consider this example. Okay, 3, 3, 3, 1. The maximum degree is exactly n minus 1 here, okay, because we have 4 vertices and maximum degree is 3, okay? And the total degree is even. So is this one graphical? 如果你的 degree sequence 是有4个 degree， 代表你有4个 vertex， 然后有其中3个它的 degree 是3。然后剩下的一个是 degree 是1，所以我要请大家试着画一下，看有没有可能画出这个图。对，我希望大家都画一下 ，OK？ 或者如果你可以直接用看就可以看得出来，它不行，那也 OK。好，知道现在要做什么事吗 ？OK， 所以你要现在要做的事情就是你要去画一个 graph， 然后如果你需要的话，前面有纸。这个 graph 有4个点，然后其中3个点它的 degree 是3。换句话说，其中有3个点它有3个邻居，然后剩下的那一个点它只有1个邻居。然后要看这样子的 graph 有没有可能画得出来。如果画得出来，我们就说这个 degree sequence 叫做 graphical。画不出来就代表它不是 graphical。你有纸吗？ This is not difficult at all. Okay, just draw 4 verses, and once you've created 3 verses with degree 3, it's all done. Okay, so very, very easy. OK， 所以是 graphical 嘛 ？OK， 所以为什么？啊，sorry， 就只有2个可以连到3个。这句话什么意思？这句话。所以哪2个可以连到3个？A B C D。OK， 所以为什么它不是 graphical？ 还是它是 graphical？ 它是 graphical， 3331是 graphical。
抱歉，不好意思。那我看到4个都可以，还有3都可以连到3个。
啊，所以。OK， 好，你想一下。所以这位同学啊，我不知道这位同学对，所以是 graphical 吗？知道什么是 graphical 的意思吗？什么叫 graphical？ 知道它的意思吗？不行，不行，对，对。OK， 所以对，所以顺带一提就是，如果 if there are multiple edges between two vertices, this is called multi-edge or parallel edge. Okay, and for this discussion, we do not allow these kind of edges. Okay. All right, so if these kind of edges are not allowed, you said that this is not graphical. Okay, so why? Okay, so you mentioned Koi. It seems like you already have an algorithm for this problem. But for this one, we don't need any algorithm. There are some simple observations you can use to conclude that this is not graphical. I will talk about the graphical, the algorithm soon, but for this one, I think we don't need any algorithm to convince yourself that this is not graphical. 所以有没有人是不需要 algorithm 的？嗯哼。
那其他的它都必须要，就是像一个 company graph 一样，
嗯哼。
要连到全部。
嗯哼。
这两件事情会产生矛盾。
嗯哼。Right. Yeah. Okay. But I think a more direct way of showing this is impossible is because now all these 4 vertices, they are like the same. Okay. So you can actually assign this 3, 3, 3, 1 in any way you like. Okay. So for example, we can say that I want A to have a degree 3, B 3, C 3, and D 1. Okay. This is our goal. Okay. If this is impossible, then there's no way you can realize the degree sequence. Okay. So now for A, it has degree 3. So you have no choice. Okay. Because you only have 4 vertices. So A, and still we don't allow self loops. Okay. So A cannot be connect back to itself. Okay. This is not allowed. So we can only let B, D, and C be the neighbors of A. Okay. So similarly, for B, it has degree 3. So we have to do the same thing. That's the only way for B to have degree 3. So similarly for C, it has degree 3. So by just considering the first 3 degrees or the first 3 vertices, we've concluded that the last one must have a degree of 3, not 1. Okay? Okay? So this is impossible. Therefore, it's not graphical. Okay. Okay, so yeah, I just want to show you that you cannot just rely on these simple checks to test whether a graph or whether a degree sequence is graphical or not. Okay. So we need an algorithm. Okay. So the algorithm has an input, the degree sequence, okay, and the output. Well, the natural output for this question is yes or no, okay, graphical or not, okay. But it turns out that the algorithm can also give you a graph that can realize the degree sequence if the input is graphical, okay. So the output will be a graph if the degree sequence is graphical, and the graph will realize it, okay? Or it will output no, it's not graphical, okay? So let's consider an example, okay? Okay, and let's see how to develop an algorithm to solve this question, okay? So for computer science, there's a very important principle for designing algorithm, and that is to simplify the task, okay? So if you can keep simplifying your task or your problem, at the end of the day, you're going to solve it, okay? As long as you have a strategy that can be applied forever to simplify the question, okay? Whenever you have a question, you have a way to simplify it. And you just keep applying this method to transform the original problem into a simpler one, okay? So for this question, we're going to use the same methodology, okay? So we want to simplify the problem. We want to make the degree sequence simpler or shorter, okay? Because if the degree sequence is it only contains 1 degree, for example. So if the degree sequence has only 1 number, then what is the only graphical degree sequence? 如果今天 degree sequence 只有一个数字，那一个数字指的是什么才可以是 graphical? Zero. That's the only graphical degree sequence. 0. So why is this one graphical? 所以为什么这是 graphical? Recall what is the definition of graphical. Graphical means we can find a graph that can realize the degree sequence. 我们可以找到一个 graph， 它的 degree sequence 就是 0。什么样的 graph， 它的 degree sequence 就是一个 0。想法吗？一个点。So this is a vertex, okay? And that's it. There's no other vertices, no other edges. Just one vertex without any edges. So this would have a degree sequence 0, okay? So, but apparently we won't face this question, okay? So if the degree sequence is 0, it's trivial, all right? Or, but anyway, let's try 2, okay? Suppose the degree sequence has 2 degrees. What are some graphical degree sequence with that 2 instead of 1, okay? 所以刚刚这个是只有一个 degree， 那现在如果有2个 degree， 那有哪一些 degree sequence 会是 graphical？ Sorry， 我听不见 ，Sorry。
就可以重复做一次嘛？
重复。Repeat my question? Okay. So my question is, what are some degree sequence that have length 2? Meaning there are 2 numbers in the degree sequence. And the degree sequence is graphical. 有哪一些 degree sequence 它里面有2个数字，而且它是 graphical？ So for a graph, for a degree sequence to have 2 degrees, it must be the case that the graph has 2 vertices. So what are some possible ways to create a graph with 2 vertices? Sorry? 0, 0 or 1, 1? Okay. So there are only 2 possible ways to create a graphical degree sequence with length 2. All right, so all this just shows that the problem is easy if the degree sequence is short. Okay? So the high-level idea behind the algorithm is that they want to shorten the degree sequence. Okay? Or make it smaller. Okay. Yeah. So given this degree sequence, what are some natural way of decrease the degree sequence? Okay. So if you want to find a graph that can realize the degree sequence, you have to create 6 vertices, okay? Because it has 6 degrees, okay? Okay. And the numbers here indicate like the target or the remaining edges that you still have to add to the vertex. Okay, so we have to add 3 edges to V1, 3 edges to V2, 2 edges to V3, and so on. Okay, so that's our goal. So I think a very, very natural way is that you just pick a vertex, okay? Any vertex, okay? So for example, we pick V1. And now, since we have to add 3 edges to V1, we add 3 edges, okay? So first we pick V1, and then we have to find 3 edges or 3 neighbors for V1, and we create the edges, okay? So now the question is, which vertices should be the neighbors of V1? 我们刚刚说，就是我们已经决定要帮 V1 找3个邻居，或找加3条边。那现在的问题是，我现在有 V2 到 V6，那哪一些点适合拿来当 V1 的邻居？我要找3个邻居，哪3个？都可以。So that's one obvious choice. Okay. So let's try this like arbitrary neighbors. Okay. Okay. So we just find 3 random or arbitrary vertices to be the neighbors of V1. And because the remaining number here is 3, so we have to find 3 arbitrary vertex. Now after we've decided, okay, V4, V5, V6 are neighbors of V1, we have to update the numbers here. So we no longer need to consider V1 because we've already added 3 edges. And for V4, originally we have to create 2 neighbors for it, but now we've already created 1. So the remaining number is just 1, okay? So all you have to do is just add 1 more neighbor for V4, okay? And for V5, and for V5 and V6, now you don't have to create any more neighbor for them because their target are 1. And you've already created 1 neighbor for them, okay? And we just repeat this process, okay? So we pick a vertex, create neighbors for the vertex, and repeat, okay? So let's see whether it works, okay? Okay, so next let's pick, say, I think now you'll see the problem, okay? So how about I pick V2? So the remaining degree is 3, which means we have to find 3 neighbors for V2. But can we find 3 neighbors for V2? Which 3?
3 and 4.
Yeah, but those are just 2. But we need 3. Right, so now you see the problem. Yeah, so we want to find 3 neighbors, but all the candidates. Here, by candidates, I mean the vertices that should still be added more neighbors into it. So V3 and V4 are the only 2 neighbors that are the only 2 vertices that are able to add more edges. So V3 and V4, just 2, but V5, V6, and V1, they cannot be neighbors of V2. Okay? So at this moment, the algorithm will say, no, this is impossible. Okay? Okay. But is the algorithm correct? Because it fails here, so your output's no. Okay. But is it true? Is it true that this 3, 3, 2, 2, 1, 1 is not graphical? Turns out that this is graphical. Okay? 3, 3, 2, 2, 1, 1 is graphical. But the algorithm, or at least precisely this algorithm, cannot output a graph that realizes the degree sequence. Okay? And the reason it fails is because at this step, so recall that here we ask a critical question. That is, after we choose a vertex, and we want to find neighbors for this guy, which neighbors or which vertices can be the neighbors of V1. So previously we've considered like arbitrary vertices, okay? Or I think you can see here that V4, V5, V6, they have the smallest degrees, okay? 2, 1, 1, those are the smallest 3 degrees, okay? So you can also say that perhaps we should not choose the vertices that have the smallest degrees as the neighbor of the chosen vertex, okay? And this makes sense because the reason that it fails here is because there are too few vertices that we can choose from to be V2's neighbors. So we want to make sure that whenever we want to choose neighbors, there are lots of candidates. There are lots of vertices that have degrees greater than 1 or equal to 1. Therefore, they can be used as neighbors, okay? So whenever you choose neighbors, you start with the one that has like the smallest degrees. Then you're going to use all these vertices like too soon because they will become 0 very fast. Therefore, the vertices they can use will be very few, okay? So what we should do is not choose these smallest degree vertices. Instead, we should start with the vertex that have the largest degrees. 所以刚刚这边很重要的事情就是，我们这边在选 neighbors 的时候，我们刚刚都选那些，应该说刚刚是乱选 ，OK？ 然后我刚刚乱选是选后面这3个，刚好这后面这3个就是 degree 最小。degree 最小的问题就是它很快就有这种0的 degree 会出现，0的 degree 出现就代表你不能选它，因为你不能再帮它加 edge，OK？ 所以我们某种程度是想要避免这种0的 degree 出现， 所以如果你要避免的话，那你就是应该去选那些比较大的 degree， 比较大的 degree 你扣1之后，因为每一次你加一个 h 就是 degree 会减1，就刚刚那位同学讲的扣1 ，OK， 这关键是扣1要扣在谁身上 ，OK， 你要扣在那些 degree 很小的身上，还是扣在那些 degree 很大的身上？所以这个 example 就告诉你说，你应该扣在 degree 大一点的身上，这样子你才可以确保你在选 neighbor 的时候有比较多的人可以选。OK， 因为刚刚失败的原因就是在这一步的时候，我就只有2个0可以当做我的 neighbor， 但是我需要3个 neighbor， 因为太多点都已经变成0。OK， 所以我有点占用大家休息的时间，我们就20分的时候再开始。OK。
因为我等一下可能有事情，可能早走。
OK， 没问题，没问题。
就这个礼拜跟下个礼拜，就第3节，可能早走，2个小时。
可以啊，没问题，没问题。
是这里吗？不能是说这样。
OK，
谢谢。
哎，是。
就是这个的差，因为上次讲的 degree 是它可能旁边的 neighbors 的话，就是像这个的话就只有两个 neighbors 嘛。
对。
但这里的 degree 的话，它反而是那个数字加总起来，是。
那这个是一个点的 degree， 然后这边是 total degree， 是整张图的 degree， 整张图的所有的 degree 的总和。
那这个
3就在这个点，它的 degree 就是3嘛，这个点 degree 是3，这个点的 degree 是3。
对，哦，好，没有，对，好，谢谢。
OK。All right, let's get started. So now let's have the correct algorithm. Okay. So step 1, we just create some vertices. In particular, we create n vertices. V1, V2, up to Vn, okay? And I'll use a variable to store these numbers below the vertices. So these are like the remaining degrees. So I'll use R. So initially, the remaining degrees are just the input, okay? Okay, so this is like the initialization step. So after that, we can start our like for loop. So in every round, we will first pick a vertex. Okay, so let's call this vertex, this chosen vertex, Vj. Okay, and we have to be careful here because when we pick a vertex, we cannot pick a vertex with remaining degree 0 because if a degree is 0 or remaining degree is 0, this means we don't have to add any more neighbors or edges. So we only need to pick vertices with remaining degrees greater than 0. And for this step, this vertex, it can be chosen arbitrarily, okay? As long as the remaining degree is greater than 0, okay? So I'll stress this by saying an arbitrary. Okay? Or just pick any, okay? Pick any vertex Vj with Rj greater than 0. Okay, and then we'll pick Rj vertices. Okay, and this vertices, first of all, it cannot be Vj because these vertices will be the neighbors of Vj. Okay, so when we pick neighbors, we cannot pick Vj. Okay, and these vertices must be must have the highest degrees, and it cannot have remaining degree 0. Okay. Pick Rj vertices with remaining degree with the highest and these degrees cannot be 0. Okay. And then we just add edges between Vj and the vertices picked in step B. Okay. And then update the remaining degrees. In particular, we're going to subtract 1 from the degree for the vertices picked in step B. Okay. And also, Rj will be 0. Okay, because we've added all the necessary neighbors for Vj. So the remaining degree for Vj will be 0. So the most important step is step C. Step B. Okay. So if we cannot successfully choose Rj versus in step B, we will output no, it's not graphical. Okay. And actually, we don't need like n rounds, okay? So as long as we cannot pick a vertex with remaining degree 0. In other words, if all the remaining degrees are 0, then we're done, okay? Because, yeah, we don't have to add any more edges. Okay. So let's apply this algorithm to the previous example. Okay. Okay. So this is after initialization. So these are R. Okay. So step 1, or step A, we'll pick a vertex with Rj greater than 0. So actually, we can pick any vertex we like. Okay. So for example, we can pick V3. Okay. So this is step A. Now in step B, we have to find 2 vertices. And this is not any 2 vertices. It has to be the one that has the one that has the highest degrees. So we'll pick V1 and V2. Okay. So this is step B, and step C, we add edges. Okay. And step D, we update the remaining degrees. So 2, 2, 0. So this is the first round. Okay, so next we can pick, again, any vertex except for V3 because V3 now has degree 0, okay? So let's pick V5, okay? Okay, so because V5 has degree 1, so this means we have to find one neighbor, and this neighbor must have the highest degree. So here we have tie, okay? So V1, V2, and V4, they all have the highest degree. So we can choose any one, okay? So for example, let's choose V4, okay? Okay, and then we add an edge, and we update the degree. Okay, so that's round 2 in a for loop. Okay, so round 3 we can do this. Okay, so we choose V1 as the vertex in step A. So now we have to choose 2 vertices with the highest degrees. So we must choose V2 because it's the highest degree. And for V4 and V6, we can choose any one of them. So suppose we choose V6. Okay. So we will add 2 edges. Okay. And then we update the degree. Okay. So this concludes this round. Okay, so next. So we can only choose from V2 and V4 as the vertex in step A. So choose V4. So in step B, we can only choose V2. And we add edge. And update the degree. Okay, so this completes this round. Okay, so in this round, when we want to do step A, you'll see that you cannot find any vertex with remaining degree higher than 0. So according to our algorithm, we will return. Okay. Okay, so we can check whether this graph realizes the degree sequence 3, 3, 2, 2, 1, 1. Okay, so V1 degree 3, V2 degree 3, V3 degree 2, V4 degree 2, V1, V5 and V6 both have degree 1. Okay, so this realizes the degree sequence. Okay. Now let's try a different example where the degree sequence is not graphical. Okay. Say, okay, so let's apply this example to the graph, to the algorithm. Okay. Okay, so this is the initialization step. And in the first round, we can choose, for example, this V2. So we have to choose 3. So we have to choose all the remaining vertices. Okay. And then we add edges. And then we update the degree. Okay. So this is round 1. Now for round 2, say we choose V1 in step A, okay? So the remaining degree for V1 is 2, which means we have to find 2 vertices in step B. And these 2 vertices must have remaining degree greater than 0. But there's only one such vertex, so you cannot do step B. In other words, step B fails, okay? Okay. Therefore, we will output not graphical. Okay. Okay, so that's the algorithm. I haven't shown that this is correct, but this is the steps that we're going to do in this algorithm. So, any questions? 有问题吗？所以应该蛮单纯的。然后背后的 idea 就是我一开始说的，就我们想办法，你可以说我们就是一个逐步满足每一个 vertex， 你也可以说就是我们一步一步，你会看到每过一个 round， 比如说我们看前面这个，每过一个 round， 它的剩下的 degree sequence 就会是越来越小。OK， 从一开始的33221到这边会变小，然后这边又再更变越来越小，然后到最后就是全部都是0。OK， 所以它就不断的把这个 degree sequence 缩小，然后到最后就结束了。OK。OK， 有问题吗？OK， 我写错吗？
The sequence is graphical, but why if the algorithm does not work and the sequence is not graphical? 就是为什么这个演算法如果失败的话，那这个 sequence 就一定 not graphical?
Right. Exactly. So that's why we need a proof. So I haven't shown the proof. Okay, but this is not trivial. So what Melvin says is that, so basically to show this algorithm is correct, we have to do 2 things. Because the algorithm can output, yes, it's graphical, or it can output, no, it's not graphical. We have to show that when the algorithm says it's graphical, it really is graphical. So that's the first point we have to show. The second one is that when the algorithm outputs no, it's not graphical, you have to show that yes, so no, actually indeed the input is not graphical. Okay? So I think when the algorithm outputs yes, it's graphical, certainly we know the algorithm is correct because we have the graph. Okay? And I think it's easy to see that the graph really realizes the degree sequence. So we don't need to care too much about the correctness when the algorithm outputs a graph. Okay, what we really need to to worry about or to think is what happens if the algorithm outputs no, okay? OK， 所以刚刚Melvin 说的是，就是我们要怎么去说这个演算法是正确的 ？OK， 你要怎么说服人家说如果我这个演算法真的有给你一个 graph， 那真的它就是可以去 realize 那个 graph。那而且当这演算法说 no， 这个不是 graphical 的时候，这个 input 的 degree sequence 真的不是 graphical， 不是只是这个演算法很笨，他没有想到一个graph 去 realize 它，是真的，就算你再怎么厉害，你也找不到 ，OK， 不可能找得到一个 graph 去 realize 那个 degree sequence，OK， 所以就我们需要去说明这个演算法是正确的 ，OK。So our strategy is like this, okay? So the algorithm will keep shortening the degree sequence, okay? So what we want to prove is that if the original degree sequence is graphical, then the simplified degree sequence is also graphical, okay? So that's one thing. And another thing to prove is that if the original degree sequence is not graphical, then after the simplification, it is still not graphical. So it's like we preserve the answer after we do the simplification, OK？ 所以我们刚刚做的事情是不断的去把这个 degree sequence 变得越来越简单 ，OK？ 那我们需要去保证的事情是，我在不断的让它变得越小越简单的同时，我不会去改变它的答案。这边的答案者是 graphical 或不是 graphical，OK？ 所以以这个例子来讲的话，33211，我们知道它是 graphical，OK？ 那我们刚刚在整个简化的过程中，我们会必须要确保说，新得到的这个 degree sequence， 它也是 graphical。OK， 你不能说本来的是 graphical， 然后变到突然间它变成不是 graphical， 那你的演算法就会出错，你的演算法就会 output no，this is not graphical。OK， 所以这是我们要保证的事情。那另外一个方面，我们要保证的事情是，如果本来的不是 graphical， 你不能变，然后突然间变成一个 graphical 的 degree sequence， 那这样子它就会 output， 它就会真 output 一个 graph 出来。OK， so it all boils down to prove this, okay? So we have the original degree sequence. Let's call it capital D, and this is D1, D2, D3, up to Dn. So this is the original, okay? And then we have the simplified degree sequence. Now for this proof, I will assume that in step A, we always choose the vertex with the highest degree, okay? So recall that for our algorithm in step A, we can pick any vertex, okay? But for the ease of presentation of the proof, I will assume that this vertex is the one that has the highest degree. And also, I will assume that the original degree sequence is in non-increasing order, which means D1 is the largest, D2 is the second largest, and so on. So Dn is the smallest. Okay. No, I think it's better to assume that, so this is still true, but in step A, we pick the smallest degree, sorry, okay? Okay. So the reason we have these two assumptions is just because we want to make this proof slightly easier to follow, okay? Okay, so this means, and also let me call this delta, because I want to write down the simplified degree sequence, okay? Okay, so if we apply the algorithm just around, okay, to this degree sequence, and we choose the one that has the smallest degree in step A, okay? So this means in step B, we have to choose delta neighbors for this guy, okay? And which delta vertices? The first delta vertices, because those are the ones that have the highest degrees, okay? So what is the simplified degree sequence? It will be D1 minus 1, D2 minus 1, D3 minus 1, up to D delta minus 1, okay? And the rest will stay unchanged. Sorry. And the last degree will be 0 because dn will be 0 after the update. Okay, let me give you an example. Okay. Okay, so in step A, we will choose the last vertex, which has the smallest degree. And so in this case, delta is 1. Recall that I use delta to denote the smallest degree. So here delta is 1. And because the degree is 1 for V6, we have to choose 1. Oh no, I think this should be 3, 3, 2, 2, 1. Okay. Okay, so in step B, we have to choose 1, the highest degree. So we will choose this one. So after the modification or simplification, the new degree will be like this. Okay? So the last degree is replaced with 0, and the first delta degrees are decreased by 1. Okay? Therefore, we have this. Okay? So the first delta degrees, they are decreased by 1, and the rest are the same. Okay? They are not changed, but the last degree becomes 0. I don't think this precise definition for D prime is important. Okay. All I want to do is to give you to make sure that to make sure that we are on the same page. Okay. That we all agree what is the original degree sequence and what is the simplified degree sequence. Okay. So you don't have to memorize this. Okay. It's not important. Okay, so all we have to do is to prove D is graphical if and only if D prime is graphical. Okay. So this double arrow indicates two directions. So first you have to show that if D is graphical, meaning the original degree sequence is graphical, then after your algorithm simplifies it, the new degree sequence is still graphical. So that's one way. Okay. The other way is to show that if the simplified degree sequence is graphical, then it must be the case that the original degree sequence is also graphical. Okay. It is equivalent to saying that if this is not graphical, then the new degree sequence is also not graphical. Okay. So basically, we have to prove two things. Okay. Okay, so between these two, which one is easier? 哪一个比较简单？大家觉得？有一个是比较从一个比较大的 degree sequence， 然后我们已经知道这个比较大的 degree sequence 是 graphical， 然后去说明，比较小的也会是 graphical， 是这个会比较容易，还是你已经有一个比较小的degree sequence 它是 graphical， 然后我们要去说这个比较大的是 graphical。这个可能大家觉得会有点抽象，所以事实上你可以去想一下，回想一下什么叫做 graphical。graphical 就代表你有一个 graph， 可以去满足这个 degree sequence。所以这句话的意思就是，有一个 graph， 我们叫 G prime 好了，它可以 realize D prime。对，这个跟这个上面这句话是一模一样。所以换句话说，当你有这个条件，就代表你有你有一个 graph， 你可以假设有一个 graph， 它要满足 D prime。OK。那这个当然就是差不多，但是是考虑 D。So let me first ask you a simple question. Okay, so now we have two graphs, G prime and G. Which graph is larger in terms of the number of edges? 就你有一个图是可以满足 D prime， 你有另外一个图是可以满足 D。那我刚刚的问题是哪一个图会比较大？然后这边的大指的是哪一个图有比较多的 edge？ Sorry， G， 对，为什么？没错，所以recall that the way we get D prime is by decreasing the degrees. So if the degree is decreased, it means the degrees are smaller. And if the degrees are smaller, this means there are fewer edges. Okay? So this is why G prime is smaller than G. Okay? So if you want to prove this direction, this is like now you have a graph, a smaller graph with fewer edges, and you want to create a larger graph with more edges. And hopefully this larger graph can realize D. Then you finish the graph, you finish the proof, okay? And for this direction, it's like the reverse direction. So now you have a larger graph with more edges, which can realize D. But now you want to create a smaller graph, okay, that realizes this simplified degree sequence, okay? So the first proof is that you want to make the graph smaller. And the second proof is that to create, to make a graph larger, okay? So I don't have time for the proof, so I'll leave it to the next week. But before that, are there any questions? 有问题吗？就今天我不会讲这个 proof。OK， 所以复习一下，我今天要让大家记得的事情就是，第一个就是 graphical 的定义。OK，graphical means there's a graph that can realize the degree sequence. More precisely, this means V1 has a degree of D1, V2 has a degree of D2, and so on. So in this case, we'll say the graph realizes the degree sequence D1, D2 up to Dn, okay? So given a degree sequence, now we have an algorithm that appears to be, be able to answer or determine whether a degree sequence is graphical or not, okay? But we're not sure, okay? So next week, we're going to show that the algorithm is actually correct, okay? When it outputs no, the input degree sequence is not graphical, okay? And when it outputs a graph, then the degree sequence is graphical, okay? And we have to prove, in order to do this, we have to do 2 proofs, okay? So that's all.